Chapter 3, this is mainly talking about moles. Also a little bit about balancing equations and also a little bit about doing stoichiometry problems. So to go ahead and get the credits done, most of this is going to be based either on Zumdahl's chemistry or on Brown and LeMay's chemistry. And the commentary here is going to be provided by myself. So this chapter only has a few things in it, but they're important because we're going to use these the rest of this semester and then all the way through. If you take Chem 1412 or organic or any other chemistry, you'll continue to use this. So it's really, really important. So what I'm going to recommend that you do is I'm going to go through just some basic examples of the things that we're going to talk about, and I recommend that you go through those over and over again until you're really, really sure that you understand these basic concepts. And if you can get to that point before the test and you have a little extra time on your hands, you can go ahead and go to someplace like Mr. Mack's website and try to do a few more problems or as many as you feel comfortable with, especially in stoichiometry, because stoichiometry gives people fits. I don't know why, because it's not difficult, but it's just looking at the relationships between the numbers in the equation, which we'll see in just a moment, but for some reason it does. So try to make sure that you completely understand the ones that we're going to do in the lecture notes and the word problems. And then if you have time, as I said, you can go to some other website or Mr. Mack's site and do some more, but don't do too many, because what will happen, I mean, just do as many as you understand it. If you try to do too many, you start getting to the point where you can't see the forest for the trees. And so what'll happen is you'll lose it and you won't be able to do any of the problems. And we don't want that. And one of the ways that I try to teach is I try to only start you off with a few very basic examples. So let's go to the next slide. So we've already talked about this. Let's go to the next slide. And this next slide. So the two really big things for Chapter 3, figuring out what is a mole of something. So you haven't probably heard that before unless you had chemistry. And then balancing reactions, and then doing stoichiometry problems. Next slide. And stoichiometry is defined as the study of the quantities that are reacting either as products or reactants. Let's go to the next slide. We'll come back to this, so don't worry about it if you don't get it. Next slide. So to kind of like introduce this, we're going to talk about counting by weighing. And that just means, like, if you have 10 balls, if you want to get an average mass, you just weigh all 10 together and divide by 10. So if you have 10 balls that have an average mass at 2 grams each, they're going to weigh 20 grams when you add all of them together. You divide the 20 by 10, you get 2. Next slide. So, for example, here's another thing just like what I just said. So we have a pile of marbles that weighs a certain amount. And then the second sentence says 10 marbles have a mass of 37.6 grams. All right, so what we can do is start with the second sentence here, this part right here. If 10 marbles weighs 37.6 grams, first of all, use that to figure out how much one marble weighs. In other words, just divide this number right here by 10, and you're going to get 3.76 grams. Or you can just move the decimal over, whatever. So that means one marble weighs 3.76 grams. We'll see this on the next slide. So divide how much all of these marbles weigh here by 3.76, and that'll tell you how many marbles you have. Let's go to the next slide. Next. So when we divide the 37.6 by 10, we get 3.76. That's the mass on average of one marble. And when we divide this number by 3.76, that tells us about how many marbles we have, and it turns out to be 105. So just divide this number that was given in the problem statement by this number right here that we figured out. Next slide. All right, so we've talked about this in the last chapter. Whenever you look at the chart and look up the mass of carbon, it won't say like 6 and then exactly 12 for the mass. It'll say 6 because it has 6 protons, and that's an exact number. But for the mass, which we're going to assume is the top number, the A number, right? You would expect it to be 12, right? Because it has 6 protons and 6 neutrons, but that's not actually the way it is in every carbon. So as we mentioned before, in that wide world out there, all the carbons, out of all of the carbons, most of them will be carbon 12. And so they'll have 6 protons and 6 neutrons. But some of them, a few, a very small number have actually 7 neutrons. So they're still carbon because they have the 6 protons. But they're not carbon-12, they're carbon-13. So we have to take that into account, and they do that on the chart. So what they do on the chart is they put the mass down that would be representative of all the carbons out in that wide world. So they have to take into account the fact that there are a few that are carbon-13, a few that are carbon-14. So the way that you do that to figure out what an average mass of a carbon would be to take what's called a weighted average, which is a fancy sounding name, but it's very simple. You just take each of the percentages of the different isotopes, like carbon-12 would be a percentage of like maybe 90%, so just change that to a decimal, which would be 0.9. Let's say you have 8% carbon-13, that would become 0.08. And if you have 2% carbon-14, that would become 0.02. Now, that's not the actual numbers. I'm just using that as an example. And then you would multiply the 0.9 times 12, and then plus 0.08 times 13, and then plus 0.02 times 14. Do you see what I'm saying? That's called taking a weighted average, and it's really just like a lot of other things in chemistry, it's just common sense. So you don't have to memorize this. You can just use your common sense to figure out how this would work. So anyway, it turns out that for carbon, when you do that, you don't get 12, obviously. You'd have to get something more than that, right? Because you've got some that's 13 and some that's 14. And it turns out that you get 12.01. So if you look at the chart, if you look at carbon, it'll say 6 on the bottom. I mean, if your chart does it in this convention, it would say 6 at the bottom and 12.01 on the top, where the 12.01 is the weighted average. So what we're talking about when we put that 12.01, it actually means two different things, and they're both completely true. First of all, what it maybe mainly means is that, although we don't use it this way very much, but it means that one carbon atom on average would weigh 12.01 units, but what units are we talking about? And so the answer to that is the units we're talking about is like if you are talking about protons and neutrons, right? Which up to this point, we've kind of considered those to have about the same mass. And actually, they do have about the same mass. But it turns out that neutrons weigh just a little bit more than protons. So if you think of like an atomic mass unit where you take like the mass of a proton and the mass of a neutron and average those so that you got yourself some kind of a mass value that would be like for an average proton or neutron. It's kind of like that. So we call that an atomic mass unit. And there are a certain number of those in like 1 gram, so you can convert back and forth. So it turns out that the way they actually do it here, which turns out to be basically the same thing as what I just said, is they define one atomic mass unit as 1/12 the mass of a carbon-12 atom, which has 6 protons and 6 neutrons. So basically, atomic mass unit would be if you added up the mass of a neutron and the mass of a proton and divide by 2. It's basically the same thing. And to convert that to something that we know how to already do, like grams, well, people in the United States don't, but people in everywhere else do. So everybody knows what grams are except us in the United States that have been here our whole lives. But anyway, to convert atomic mass units to grams, you have this little simple conversion here. One atomic mass unit is 1.66 times 10 to the minus 24th grams. Next slide. So here's what we just talked about. So actually it turns out that, so here's what we just talked about doing. We said that we were going to multiply the percentages of carbon-12 times its mass, which is 12, plus the percent of carbon-13 times its mass, which is 13, plus the mass, the percentage of carbon-14 times its mass. And when you do that, as we'll see on the next slide, you get down at the bottom right here, we get 12.01 atomic mass units, and that mu, that Greek mu, stands for atomic mass units. So it's just an abbreviation. It's just an abbreviation for AMU, which in turn is an abbreviation for atomic mass units. So mu, to come back down here at this thing here, that's a Greek letter M. It's the lowercase. So all the Greek letters have at least an uppercase and a lowercase, and sigma actually has 3 different forms. And we use all of them in science, I mean, for the sigmas. So in this case, this is the lowercase Greek letter for our M. Okay, so let's go to the next slide. So I'll let you read this on your own. Kind of interesting. Next slide. So here's a chance for us to do it. So I recommend you try to do this without looking at the answer after. I mean, I'll tell you how to do it, but then try it on your own later and make sure you know how to do it without looking at the answer. So what we have here is we only got 2 isotopes of this, and that's not probably going to happen. But so we have 62.6% of one that weighs this many atomic mass units, and then we have 37.4% of another isotope, and it weighs this much. And so what would you put on the periodic chart if you were doing this? And I can tell you right now it wouldn't be this easy, because some of those, especially the larger elements, are incredibly difficult to do. All right, so let's just do this. So what we want to do is we want to convert percentages to decimals, so move the decimal place back 2 places to the left, and we have 0.626 as the decimal, which will be multiplied by this number over here. And then plus, we want to add that to 0.374, which is the decimal form of 37.4%. So just converting percentage to decimal, just move the decimal place back 2 places to the left, get rid of your percent. You have 0.374, and then multiply that by this mass over here, and then add them together. So let me say it again. So 0.626 times 186.956 plus 0.374 times 184.953. Again, this is the Greek letter mu. It looks like they just used a U here, which is close enough, I guess. All right, let's go to the next slide. Next. Okay, I couldn't get it to go forward. So here is what we just said we were going to do. So here it is done. So 0.626 times 186.956 plus 0.374 times 184.953. And when you do that, on your calculator, you should get 186.2. Again, be real careful when you're typing this stuff into your calculator. So I recommend that you do it really slowly. And then to figure out that it's rhenium, what they evidently did here was they looked on the chart and they said, okay, which one of the elements on the chart is close to 186? And they figured it was rhenium. And so that's okay for this course, but in actual nuclear physics you can't do that, because there might be 10 different elements that could possibly have a mass or more that could have a mass of 186 because of isotopes. But for right now we'll just forget that. So go to the next slide. Okay, next slide. All right, so it turns out that what we really need to do is we need to figure out some way to convert back and forth between things at the atomic level and things at the level we can actually measure. We can't measure the mass of a carbon atom directly. It's too small. So people did some experiments. They said, okay, let's see, for example, for hydrogen, it has a mass of 1 because it's got 1 proton. So its mass is an atomic mass unit, 1 atomic mass unit. So let's just see how many hydrogens there would be if we, I mean, just to make it easy, let's just weigh out 1 gram of hydrogen, and it has to be H hydrogen, not H2. So we weigh out 1 gram of hydrogen. Actually, they probably didn't use hydrogen because it's diatomic. So maybe let's think about the possibility they could have done something like carbon, but let's stick with our example of hydrogen just for the sake of argument, even though they may not have actually used it, but it doesn't matter, as you'll see in a moment. So if you weighed out, it turns out 1 gram of hydrogen, and then you count how many atoms of hydrogen are in there. If you could do that, which you couldn't, because it would be too big of a number to count. But if you could do that, you would find that there were 6.02 times 10 to the 23rd atoms of hydrogen in that 1 gram of hydrogen. So they might say, well, let's do the same thing for carbon. Okay, so let's go to carbon. So for carbon, if you weighed out 12 grams of carbon, and the reason you're weighing out 12 is because you're trying to find some way to go back and forth between what the atomic mass is on the chart and what the number of AMUs or nucleons is in the atom itself. So if you, again, look at the chart, Carbon has a 6 at the bottom and a 12 at the top, right? It's 12.01, but we'll just round that. So 12, so weigh out 12 grams of carbon and how many atoms would be in there. And it would be the same number, weirdly enough. But actually, it turns out it's not really weird because there's actually a reason for it that's very logical. Nitrogen has number 14, right? So if you look at the chart, if you got, I mean, I recommend you keep a chart with you when you're listening to these, if you can, if you're not driving or something. Then if you look at nitrogen, it's 7 and 14. So if you weighed out, let's just say 14 grams of nitrogen, how many nitrogen atoms would you have? And it turns out you'd have 6.02 times 10 to the 23rd. Well, if you did that for anything in the whole chart, it's going to give you the same number. It's always going to be 6.02 times 10 to the 23rd, and there's a reason for that, and that is that because every one of those atoms is made up of things that have masses in atomic mass units, and one atomic mass unit is 1.66 times 10 to the minus 24th grams. We talked about that about 3 slides back. And so if you take the reciprocal of that, you get your 6.02. So if you divide 1 divided by that, you get 6.02 times 10 to the 23rd, which means that every time you have one atomic mass unit, which that's where the 1 comes from, and if you divide it by the number of grams in that, you get the number of atomic mass units. But so, for example, for carbon, you would get that same number, but it would be divided by 12, but then you multiply it by 12 because you're going to take 12 times as much when you do it to start with. So what you're doing basically is this. Look at this. You're taking the chart, you look at the chart, and you get the approximate rounded to the nearest whole number here. So carbon would be 12. So what we're saying here is that if we have 12 grams of carbon, we have this many atoms of carbon. And it works that way for anything in the chart, as I said. And it even works if you're doing molecules. If you took, for example, water is H2O, right? So O is 16. If you look at the chart, its atomic mass is about 16. I think it's 15.99. We're going to round it. Plus 2 H's, which are 1. That's 16 plus 2 is 18. Then if you, what we're saying here is if you massed out or weighed out 18 grams of water, which that's actually something that's more like what we could actually do because these gases are harder to work with. If you mass out 18 grams of water, you've got one of these 6.02 times 10 to the 23rd, in that case, molecules of water. CO2, if you massed out 44 grams of that, you'd have 6.02 times 10 to the 23rd molecules of CO2. All right, so we have a name for this thing so we don't have to keep saying, 6.02 times 10 to the 23rd. We just say 1 mole, where the mole comes from the first 4 letters of molecule. So it's not the same thing as molecules. It's a special thing. And also this number has a special name. It's called Avogadro's number. So they're all 3 like synonymous. Avogadro's number is 6.02 times 10 to the 23rd. So when you have 12 grams of carbon, you have 6.02 times 10 to the 23rd atoms of carbon, or you can say 1 mole of carbon. All right, so if you didn't quite get all that, it'll come to you hopefully as we keep going. So let's go to the next slide. Next slide. Next slide. So, I mean, if you want to pause those previous slides, calculate the number of iron atoms in a 4.48 moles. So we just said that 1 mole is the same thing as 6.02 times 10 to the 23rd. So if you have 4.48 moles, you would just multiply 4.48 times 6.02 times 10 to the 23rd, and that will tell you the number of atoms in that sample. Next slide. This thing is not clicking. Okay, so multiply the 4.48 moles times the 6.02 times 10 to the 23rd atoms per mole, and you get 2.6969 24th atoms. And then if you round it off, 2.70 times 10 to the 24th atoms. Next slide. So molar masses are what we call when we do this. So for example, if you have H2, then its molar mass would be 2, because H is 1 because it has a mass of 1, but if you have H2, gas, then each one of those H2s has 2 times 1, which is 2. Water's molar mass would be 18. So let me just try to write this real quick here, because it's just, see, that's what happens when I try to write with this thing, is that first of all, sometimes it doesn't even pick up, and then other times it's hard to get the lines to go the way I want them to go. That's supposed to say H2O, and then I'm going to draw an arrow and I'm going to write just 18. And what that actually is 18, well, two different things. It's actually 18 atomic mass units, right? So there's 16 atomic mass units on the O, and then 2 hydrogens each, which has 1. So 16 plus 2 is 18. So it would be able, you would be able to write this as 16 atomic mass units. However, it also means something else, which we didn't talk about this yet, so let's do that now. It means atomic mass units because there's like basically 18 protons and neutrons in H2O. But it also, because of what we said a minute ago, can be written as 18 grams in 1 mole. Because remember, we said that we were going to relate 18 atomic mass units to 18 grams, which is something we can measure, right? So if you had 1 mole, if you had 6.02 times 10 to the 23rd of these, then you would have 18 grams. So we say that water has a molecular mass, or a molar mass, those are kind of used interchangeably, of 18 grams per mole. So if you're not getting this, what you should do maybe is pause it and replay it over and over again, so that, because I can't really just stop. But this is actually kind of profound, so you may want to do that. All right, so for nitrogen, if you look at the chart here, right here where I'm drawing the box, it's 14.01. We're going to round these, though, except for a few, like chlorine, we're not going to round because it kind of goes right in the middle. But most, and magnesium's that way too. But most of these we're going to round. So we would round this for our problems to 14. The molar mass of nitrogen would be what we would also call it the atomic mass, because nitrogen by itself is just an atom. So it would be 14 grams per mole. So there's two different ways you can say it. You can say that nitrogen has a mass of 14 atomic mass units in one atom. That's 7 protons and 7 neutrons. Or you can say that if you had 14 grams of it, you'd have 1 mole. So another way of saying that is it weighs 14 grams per mole. Okay, so water would be 16 for O, which is here. It's actually rounded to 16, and then 2 times 1, so that's 18. So we wouldn't worry about the O2 here. Now you can if you want to, but you're just making life difficult, because what's going to happen is a few of these are going to be like this. They're going to be a little bit less and a little bit more for some of them, like this one, and they even out. Just like if you're doing your checkbook, when you balance your checkbook, or on IRS returns, you can just forget the cents because they have a tendency to cancel each other out. And then for barium nitrate here, down at the bottom, what you'd have to do is look up the masses for each of these and multiply them by how many there are. So notice here for barium, you would look that up on the chart. It's 137.33, and since the 3.3, since it's not like just below or just above a whole number, just leave it in there. Just, there's only a few of these that are like this, so we'll just put up with those. Like I said, chlorine is another one, and magnesium is another one. Chlorine is 35.5, we're going to call it, and magnesium is 24.3, and there may be a couple of others. But the other ones, mostly you can just round to a whole number. So anyway, we would use the 137.33 for the barium. And then for nitrogen, it's 14, but we have 2 of them, because everything in this parentheses here, there's 2 of them because of that 2 subscript right there. So we would multiply 2 times 14. When you look up nitrogen in the chart, you have to be careful and get the right number. You don't want the 7 number. Again, if you've got a chart, if you'll just look at it, nitrogen has a 7 and a 14 associated with it. You want the 14 in this case because we're dealing with the mass, not the atomic number. So 14 times 2 would be 28. And then if you look at O, it's 16, right? The top number. But how many do you have of those? So take a look at this for a minute and see if you can figure out how many O's each one of these barium nitrates would have. Well, it would have 3 because every N has 3 O's. But then the whole thing has to be multiplied by 2 because there's 2 of the nitrates. So how many O's would you have total? Well, you'd have 6. You'd have 3 times 2, which is 6. And we're going to call O 16, so you'd have to multiply 6 times 16. And that would be 96. So you'd add 96 plus the 28 here for 2 times 14 plus the 137.33, and you'd get 261.35 grams per mole. Okay, so a lot of the problems we'll do for the rest of general chemistry, part of the problem will be just trying to figure out what the molar masses are. A couple of times they'll tell you what they are, but most of the time they don't. Okay, next slide. And then what this slide is basically telling you is that even though things like sodium chloride are ionic, and they don't really make molecules, right? And we've talked about this quite a bit before. So we call that we look at a lattice that's NaCl, and we just take one Na and one Cl, and we kind of like mark them and say this is one formula unit. So when you're doing calculations that have something like NaCl, you just assume that one NaCl thing is going to be the same thing as like a molecule. So you just add them together. So here you can see at the bottom, the Na is 23 and the Cl is 35.5, and we're not going to round that because it's like right in the middle. So for NaCl, the formula mass would be 58.5 AMUs. Otherwise, it's just the same thing as molecules. Next slide. So which of the following is closest to the average mass of one atom? So if an atom is really, really tiny, then one atom, this isn't really the way you would do this problem, but for this particular problem, you can just look here. See, there's no way that one atom is going to weigh 63 or 52 or 59 or 65 grams. They're going to weigh a tiny, tiny part of a gram. Remember the conversion factor was 10 times 10 to the minus 24th grams. That was for hydrogen. Well, copper is bigger than hydrogen, but it's still going to be really small, so we can just look at this and see that this is going to be the answer here. However, if you wanted to figure it out exactly, you would multiply the mass of copper, which is 63.55 actually, times the mass of 1 AMU, which is 1.66 times 10 to the minus 24th, and you would get this number right here, and that's actually done on the next slide. So here is the way you actually do this. You multiply this times this, and your conversion factor here, and you get 1 point, they've actually got this turned the other way, but anyway, you get 1.056 times 10 to the minus 22nd grams. Next slide. Next. Calculate the number of copper atoms in 63.55 grams. So if you look at your chart, again, find copper. It's going to be in the transition metals in the middle. One copper atom has a mass of 63.55 AMUs. But remember, we also said that we can say that that means that if you had 63.55 grams of copper, you would have 6.02 times 10 to the 23rd atoms of copper. Or we could also say we'd have 1 mole of copper. So that answers this question without having to do any more work. If you have 63.55 grams of it, you've got 6.02 times 10 to the 23rd atoms of copper. And you can see how long it takes me to write anything with this thing. Okay, anyway, that's our answer. Next slide. All right, next slide. Having problems with this thing. Which of the following 100 gram samples contains the greatest number of atoms? All right, so what you would do here is, first of all, you look up the mass of magnesium, which I think is 24.3. Zinc I don't remember, and silver I don't remember, but anyway, we'll see it on the next slide. So you look up the masses, and then you'll want to remember this rule. So you may want to write this down or just try to commit it to memory. What you do to get the number of moles, which is what we're going to actually have to do here, even though it says number of atoms, what we're really going to have to do here is get the number of moles. And that's the way it'll be the whole semester, so that's the way you want to learn it. We want to find the number of moles, because once we know that we know the number of atoms, we just multiply by 6.02 times 10 to the 23rd. So what you would want to do is look up the masses for each of these, which I'm not going to do it right now because I want to tell you how to do this first. So whatever it is, like for magnesium, I know it's 24.3, which I didn't write the 0.3 because it takes too long, but you would divide how much, here's your rule, you divide how much you have, which in this case is 100 grams, by how much 1 mole weighs, which is 24.3. And I'll say it again because you're going to really need this. You divide how much you have by how much 1 mole weighs. How much you have divided by how much 1 mole weighs. So in this case, how much do you have? You have 100 grams. How much does 1 mole of magnesium weigh? For part A, 24.3 grams. So that's what, about 4 moles, right? And then you would do the same thing for zinc. So figure out from the chart how much it weighs, the larger the two numbers, and then the same thing for silver, and figure out how much it weighs. And then divide 100 by the mass of zinc to get the number of moles of zinc, and then divide 100 by the mass of silver to get the number of moles of silver. And then that basically will answer your question. And then actually, if you want to do it exactly the way they're asking here, you're going to get the same answer anyway, but then you would multiply each of those 3 numbers you just got of number of moles, multiply all of those in turn by 6.02 times 10 to the 23rd, but that won't change your answer because whichever one has the largest number of moles is also going to have the largest number of atoms, right? Next slide. So let's see, zinc was 65.4, so you would have about 1.3 moles of zinc. So let's just write an approximate number. So this one's going to be about 4 moles. And I'm getting that 4 by dividing 100 by 24.3. And I know it's not exactly. And then for this one, it's going to be about 1.33, or let's just write 1.3. And then for silver, it's going to be a little bit less than 1, so let's just write 1. And again, for silver, I'm dividing 100 by 108. So compare those 3 numbers, which is largest. The 4 is largest, right? So magnesium is going to be the one that has the greatest number of moles, and therefore it has to have the greatest number of atoms. Next slide. Next slide. Rank the following according to number of atoms greatest to least. So you just do this the same way. So here, if I'm remembering correctly, I think that's exactly the mass of silver on the chart. So that means you would have 1 mole of silver. Zinc, I've already forgotten. Gosh, I think it was like 65. So this means you would have a little bit more, like, and I'm just going from memory here. It should be like 1.03. And this is just something I'm doing in my head. And then for magnesium, magnesium was 24.3. I remember that one. So if you only have 21 grams of it, you divide how much you have, which is 21, divided by how much 1 mole weighs, which is 24. So that's going to be like 0.9. So the one that's going to have the most is going to be, if I'm doing this right, is zinc. And then silver, and then magnesium. Let's go to the next slide though and get it right. So yeah, and I was actually off a little bit on the magnesium, but it was close enough. So the zinc is going to be the largest. And again, I'm just doing this number of moles because it's going to give you the same answer either way, because they're just asking which one's going to be the most. So the one that has the most moles is going to have the most atoms. Again, you would just multiply all of those numbers of moles by 6.02 times 10 to the 23rd. So this one is going to be the highest, and then the silver is going to be next because you had exactly 1 mole of that, and magnesium is last. Next slide. Next. All right, so this one, consider separate 100-gram sample of each of the following and find them according to the number of oxygen atoms. All right, so for this problem, you have to do 2 steps. First, you have to see how many moles of this you have, how many moles of this you have, and so forth for all of them. To do that, you divide how much you have, which in all these cases is 100 grams, by how much 1 mole weighs. Okay, so let's go back over here to H2O. How much does 1 mole of H2O weigh? It weighs 18 grams, where I'm getting the 18 by adding 16 for O plus 2 times 1 for H. For nitrogen, it would be 44. 2 times 14 is 28, and 28 plus 16 is 44. CO2 is also 44. 12 for carbon plus 2 times 16 is 44. So N2O and CO2 are going to have the same number of moles. So for the first step, what you want to do is find the number of moles. And I'm just going to write M there. So first of all, find the number of moles. And then we have to do something else in this one. They're not asking for the number of moles as they did before. They're asking for the number of O atoms. So for each one of those, what you have to do is you have to multiply the number of moles times how many O atoms are in the molecule. So here, for example, there's 1. Here, so you'd multiply whatever number of moles you would have, which is going to be about 5. You would multiply it by 1, so it'd be 5. Here, 40, it's going to be 2 point something multiplied by 1. Here you're going to have 2 point whatever, 2.1 or 2.2, but it's going to be multiplied by 2 because you've got 2 O's in every one of the CO2s. And then here, let's see, 32 and 36, 68, 74, so you've got about 1.3, and then you have to, moles, and then you have to multiply that by 2. So you've got 2.6 here. Here you have about 2 times 2 is 4, so this one is going to be, let's see, yeah, CO2 is going to be the most. Next slide. Whoops, what did I do wrong? Okay, so for H2O, let's see, number of oxygen atoms. Okay, correct. So for the H2O, there's only 1 O there, but there were 5 moles. Okay, so actually the CO2 would be the second most, and the H2O would be the most here. So for H2O, we have 100 grams. We divide it by 18. We get about 5 moles of H2O, each of which has 1 O. So when you multiply the 5 times 1, you get 5. So that's actually more than what you get here, where you got about, what, 4 or something like that. Actually 3. So anyway, when you multiply these out, you're going to, anyway, CO2 would actually be the second most, and then this one turned out to be the third most, and the N2O is going to be the least. Next slide. So for this class, as we've mentioned before, we're going to round off all of the atomic masses except for just a handful. And so here are some of the ones I've already mentioned. For magnesium, we're going to do 24.3. For chlorine, we're going to keep it at 35.5. For zinc, and I think we've already done all of these, right? 65.4. And for copper, 63.6. Otherwise, just round them off to the nearest whole number. Next slide. All right, next is mass percent, and this is very simple. So this is one of the only times in chemistry where we worry about how many grams something weighs or the mass of it rather than the number of moles. Most of the time we're going to change to moles, as we'll see here as we go through this chapter. So mass percent is just the mass of, for example, here if you've got a compound like H2O, it would be the mass of the thing that you're looking for, which could either be the H or the O, divided by the total mass. So for example, if you've got water and you want to know what the mass percentage of the hydrogen is in the water, then what you could do is divide the mass of the hydrogens by the total mass of the water, which would be, my fan just died, 2 divided by 18. So 2 divided by 18 is 1/9. That's 0.11, so it would be 11%. So for water, if you wanted the mass percentage of H, it would be 11%. For the one that they give us here, iron oxide, you want to look up the mass of iron in the chart, which is about 56. And then, of course, you know O. Hopefully, you'll want to remember O is 16. So 2 times 56 is 112. Plus 48 would be 160. So this whole thing weighs 160. And then if we want to know what the mass percent of the iron is, we would divide 2 times 56, which is 112 roughly divided by 160. That's all you have to do. So just divide how many grams you have of the thing you're interested in, which in this case is the iron, divided by the total mass. So in this case, it's about 112 divided by 160. And then you're going to get a decimal, which is going to be like 0.6994, and then to get it to percentage, you multiply by 100%. Next slide. All right, so consider separate 100 gram samples of each of the following: H2O, N2O, C3H6O2, and CO2. Rank them from highest to lowest by percent by mass of oxygen. So here we can just look at this first one and see that oxygen is almost all of the mass of water, because oxygen is 16 and water is 18. So that's like what? 16 divided by 18 reduces to 8/9, which is like 88% of water is made up of oxygen. So that's what you would do for all these. So the 16 here is the mass of O, the 18 is the mass of water. And then do the same thing for all of these. Let's come over to CO2 here. So if you want to do oxygen for the CO2, you would have 32, because you've got 2 of them here. And then divide it by the total mass, which is 44. So that's about roughly 0.75%. And then to change 0.75, which is 75%. So this one is going to be about 75%, but the O's in water are even more than that. That one's about 75. This one's about 88, though. So this one's going to be number 1 here. CO2 will probably be number 2, and N2O will probably be number 3, but I'm not going to go through all of these just for the sake of time, because we're already up to 40 minutes and we still have a long ways to go. And actually, some of the stuff we still have to do is actually the harder part of the chapter. So let's go ahead and move on to the next slide. You can go ahead and finish this on your own. Here are the answers. And it turns out that the H2O was about 89%. CO2 was 73%. So those were the most. Let's go to the next slide. Next slide. All right, now on to empirical formulas. There are 2 different kinds of formulas. So for example, for the compound called benzene, the formula for that is actually C6H6. So if you look up on the internet the formula for benzene, you'll see C6H6. Had to turn on a different fan because it's just absolutely roasting hot in here. All right, so we call this the molecular formula for benzene. It's C6H6. That's what it actually is. Benzene actually looks like this, where each one of those angles is a carbon atom. There are 6 of them, so you've got 6 hydrogens in each of those, 6 carbons, and each of those carbons has a hydrogen sticking off like that. So you've got 6 hydrogens also, and there's some double bonds in here also. And it's usually just drawn this way for simplicity. The empirical formula is what you would get if you took the C6H6 and divided it by the largest common denominator, which is 6 here, or the largest common multiple. So you divide both C6 and H6 by 6, and you're just going to get what? You're going to get C1H1, or just CH. So we call the empirical formula the CH here. So the CH is the empirical formula, and the C6H6 is the actual formula, or the molecular formula. So we'll have some problems where we're going to have to figure out what is the empirical formula. So for right now, just remember that the empirical formula is going to be the one that is reduced to the lowest number in terms of the subscripts. So we're going to have some problems where we'll first of all figure out what the empirical formula is. And then what we'll do after that is, in some cases, we'll have to figure out what the molecular formula is. Next slide. All right, so here's an example of this. We're supposed to find the empirical and the molecular formula, and we're given that the composition of this adipic acid, which don't worry about what it is 49.3% carbon, 6.9% hydrogen, and 43.8% oxygen. So there's a trick to doing these problems, so you probably want to write this down, and that is that what you want to do first is you want to assume that you have 100 grams. Now what we have is actually 100%, right? But you want to assume that you have 100 grams and then divide accordingly. So if you had 100 grams total of this stuff, then 49.3 grams of it would be carbon, and then 6.9 grams would be hydrogen, and 43.8 grams would be oxygen. Okay, so to do this kind of a problem, you always want to approach it the same way. So if you can just remember how we're doing this one, you can do any of these. So what we're going to do is we're going to go ahead and go through a few steps to find the empirical formula, and then we'll use that and figure out what would the mass of this thing be if we had the empirical formula, and then see if it matches the molecular formula. Sometimes they won't ask you to do that, sometimes they will. So if it doesn't match the molecular formula, then you usually, or always really, you can just get it to the molecular formula by multiplying it by some small number. Like, for example, to go back to the benzene we talked about before, when we figured out the empirical formula, we said it was CH. But if we looked at the mass of CH, that would be 12 plus 1, which is 13. It turns out that it wouldn't actually be matching what it would be for the molecule, because the molecule would be 78. So we would just divide the 78 by 13 and get 6, and then multiply both by 6, and we'd end up with what we started with, which is C6H6. So that's what we're going to do here. So here are the steps. First of all, assume you have 100 grams, and then change the percentages to grams. So for carbon, again, as I said before, you want to change that from 49.3% to 49.3 grams. So do that for all of them, and then divide by how many grams are in a mole, how much 1 mole weighs for each of them. So for carbon, here you would have 49.3 grams of it, and then you divide that by 12 grams per mole, and you're going to have a little bit more than 4 moles of it. For hydrogen, you're going to have about 7, and for oxygen, you're going to have between 2 and 3. And then what you want to do, and this is the one that's a little harder to remember, okay? So what you want to do at this point is you want to divide through by the smallest number that you got, which in this case is going to be the number that you got for the O here, because this one's about 7, this one's about 4, and the O is going to be between 2 and 3. So you divide through all of those numbers you just got, the mole numbers. There's 3 of them, right? 1 for C, 1 for H, and 1 for O, and you divide all of them by the lowest number. And that's something you're just going to have to remember. So it means something that you'll just have to put on your things to memorize sheet. And then once you've done that, that's going to give you your empirical formula. So let's go ahead and look at that on the next slide. So here, what I've done is I've assumed that there was 100 grams, and then I divided through each of these by the number of grams per mole. So for example, for carbon, I got a little more than 4 moles, and for hydrogen, I got 6.9 as expected. And then for O, I got 2.7375 moles. Again, I got this by dividing how much I had, which was 43.8 grams, divided by 16, which is the number on the chart. And then you divide through all 3 of the numbers that I just underlined here, 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 and then here, by the lowest, which in this case is the 2.7375. So when you divide 2.7375 by itself, you're going to get 1. So that one's going to be 1 for the O. Let's go to the next slide. And then when you divide through all of these other ones here, where you're dividing through by that whatever it was, 2.7375 or whatever for O, then you're going to get these values that I have at the top. So you're going to get 1, obviously, for the O, because you're dividing the same number by itself. When you divide the 7 that you had for H by that number, you get 2.5 for hydrogen. And for carbon, we had a little bit more than 4 divided by the 2.73 gives you 1.5. So if you wanted to write this out now, you could. Here you could write, like, for example, you could write C 1.5 as a subscript, H 2.5, and O 1. So you would write it as C sub 1.5, H 2.5, O. C 1.5, H 2.5, O. However, usually, I mean, you want to change it because you don't want to have fractions in your empirical formula, because you can't have half of a carbon atom. So the easiest way to fix that is to multiply all these numbers, all of them. You can't just multiply the ones that have the 0.5s. You have to multiply all 3 of them by 2. If you had, instead of 1.5, if you had 1.33, then the way that you would get rid of the 0.33 would be to multiply 3 by 3. But you have to do that for all 3 of them. All right, so what would we have if we multiply through by all of these by 2? This is going to become 2, O. C is going to become 3, and H is going to become 5. So our formula would be what I'm circling right now. It would be C3H5O2. And that is the empirical formula. Okay, so what we would want to do now is we want to compare how much one of these would weigh, that I'm pointing to right now, as opposed to how much the actual molecule weighs. So we were told the actual molecule has a weight of 146 grams per mole. And that was something they gave us in the problem statement. So let's add up and see what we have if we find the mass of what we just did for the empirical formula. So we're going to want to add 3 times 12 plus 5 times 1 plus 2 times 16. And when we do that, we get 73. So this thing that we just figured out, the empirical formula, weighs 73 grams per mole. But the actual molecule weighs twice that much. It weighs 146. So in order to get the formula for the actual molecule, everything in here, the 3 and the 5 and the 2, all have to be multiplied by 2. Okay, so the C becomes 6, the H becomes 10, and the O becomes 4. So the answer to part B would be C6H10O4. Next slide. All right, very briefly, patterns of reactivity. You can divide reactions into several different kinds, and these are not all of them. These are a few of them. So one main group of reactions is where you take two things and add them together and make one thing. So here we're taking 2 magnesiums and an oxygen, and we're making magnesium oxide. So that's called a combination reaction. Another one is just the opposite of that, where you take one thing and break it up into 2 or more things, usually 2. So that's called the decomposition reaction. And then you have another kind called the combustion reaction, where you're burning something. And we've talked about combustion before. Let's go to the next slide. We have some examples here. Here are some examples, legitimate examples of combination reactions. All of these are taking 2 things and adding them together to get one thing. But it's not just like you're just adding them, you're actually rearranging these things. So it actually is chemical reactions. Decomposition, here are some examples of that, and then I'm going to go to the next slide. You can pause and look at this if you want to. For combustion reactions, remember we said last time, I think it was, that always you have the same products when you burn something, like a hydrocarbon. So you're starting off with like CH4, which is methane gas, and you're always going to be reacting it with the same thing. And what do you remember what that was? What's always present whenever you burn something? I mean, unless you're doing it in like a sealed container. Oxygen, right? Oxygen that's in the air. So you're always basically reacting oxygen, even though it doesn't seem like you are, but you actually are reacting oxygen with your hydrocarbon, and you always get the same 2 products. And do you remember what they were? It's always going to be H2O and CO2. Okay, so, and the reason I'm saying that over and over again is because you'll need to remember that. Next slide. All right, now let's go to balancing. This is one of the main topics here, and goodness, we're already at almost an hour, but let's go ahead and get into this. So balancing reactions just means that you're trying to make sure and making sure that you have the same number of atoms of each element on both sides of the reaction arrow. Let's go to the next slide. So for example, here's your arrow that's dividing between the reactants over on this side and the products over on the right over here. So what we want to do when we balance a reaction is make sure that we have, for example, the same number of O's on the left that we have on the right. So let's just do that right now. So here, if you want to count up just the O's first, we have 1 there, right? And we have 6 here, because we have 3 O2, so we have 6. So we have 1 plus 6 is 7 there. And then here we have 2 times 2 is 4. And here we have 3 times 1 is 3. So we have 7 O's on the right. So we have 7 O's on the left and 7 O's on the right. So for O, this reaction is balanced. Then we could do the same thing for the C's. We can see that we have 2 C's on the left and 2 on the right. And then the H's, we have 6 and 6. So this reaction is balanced. So what they'll do typically on the final and on other exams is they'll give you the same reaction right here, but they won't have the numbers there. They won't have the 3 and the 2 and the 3. So you have to put that in. Okay, next slide. Before I go to the next slide, let me just say one more thing. So whenever you have something like this, where you've got something by itself here, like the O2 we have here, you want to leave that to last, so that whenever you get everything else balanced, you can easily come in and just put a number in front of the O2 to fix everything else. So for the O. So let's go to the next slide. So next slide. All right, let's just stop for 1 second here. The balanced equation represents an overall ratio. So what we call this is the numbers in front of those things in that previous slide are called coefficients, and that's down here at the bottom. So those numbers like the 2's and the 3's are called coefficients, and the relationship between the numbers in front of like the reactants and the products, so two different reactants, the ratio or the relationship between those two is called the stoichiometry, which we'll come back to that. Next slide. All right, so here's a little sheet that tells you what to do to balance, which I'll let you read this at your leisure. Next slide. So let's go ahead and look at this one very quickly because we're going to have to actually move ahead here. So I spent maybe a little bit too much time on the first part of this, but that's okay. We'll get through it. So what we're supposed to do now here is we're supposed to balance this thing right here. So let's do that. So first of all, look at your calciums. Calcium, we have one on the left and one on the right, so it's already balanced. So now go to your carbons. Carbon, we have one on the left, and notice here that this carbon's by itself, so we're going to leave that to the very end. But if we look over here on the right, we see that we have two carbons here and one carbon over here, so we have a total of 3. So the carbons are not balanced. So let's go ahead and do the O's, and we'll come back to carbon at the end. So O's, we have one on the left over here, and we have 2 on the right. So we need to have 2 on the left. So the way that we can do that is to put a 2 right here, okay? And now the calciums are not balanced because we messed them up. So this is one of the frustrating things about balancing equations, is that when you have something that's right, sometimes when you have to balance something else, you mess up the thing that was okay before. And that's what happened here with our calcium. So now we have 2 calciums on the left and only 1 on the right, so we have to come over to the right-hand side of the arrow and put a 2 right there. And you'll notice when I wrote this out or typed it out that I left spaces where I could put the numbers in. All right, so now let's see what we've got. We've got 2 calciums on the left, 2 on the right. O's, we have 2 on the left and 2 on the right. So the only thing left is the carbons. So we're going to leave this carbon right here to the very end, and we're going to count how many carbons we have on the right and match it here in front of this carbon. So how many do we have on the right? We have 2 times 2 is 4, and then we have 1 here, so we have 5. So that means we need to put 5 here and we're finished. 5, and that's, apologize for writing that on top of the C, but that's supposed to say plus 5C. And we're done. So which one of these answer choices is correct? We'll come down here and you see that answer choice 2 matches what we just said, but is that the only one that matches? So let's look at 3, and it turns out that we can go from 2 to 3 here. I mean, maybe this isn't the ideal way to introduce this, but we can go from 2 to 3 by just multiplying all the numbers in 2 by 1/2. This is actually also correct. It's just that 3 down here, I mean, it's technically correct, but usually people don't write them that way, although they do sometimes. But you try to avoid fractions. And so this one has a 2.5 and a 0.5. So you would usually write it the way that I'm going to make a big check here. And then also we can look down at 4 here and see that it's another way that we can write 2 by multiplying everything in 2 by 2. 2 times 2 is 4, and so forth. We get 4. So answer choice 4 is also correct. However, answer choice 1 is not correct, and the reason is because what they did was they actually changed CaO by putting an O2 here, where a 2 is a subscript on the O, and you can't do that because you're actually changing the chemical structure, and that's not allowed because that's not what's actually happening here. You're starting really with CaO, not CaO2. So number 1 is out. It's like basically verboten. So get rid of that. And so that means 2, 3, and 4 are correct. Let's go to the next slide. So next. So here's a concept check. Which of the following are true concerning balanced chemical equations? There may be more than one true statement. Number 1, the number of molecules is conserved. That is totally not true because you could vary that tremendously. So the molecule number has nothing to do with it. You're trying to balance the number of atoms on each side. Number 2, the coefficients tell you how much of each substance you have. And what they mean by this is how many grams you have, and that's obviously not true either. It's telling you how many in the actual equation how many atoms or molecules you have, and then if you want to look at it in terms of the grams per mole, it's telling you the relationship between the number of moles of the reactants and products, but not the mass. Number 3, atoms are neither created nor destroyed. That's true. That's the only one that's true so far. Number 4, the coefficients indicate the mass ratios of substances. And again, there's that word mass. And we very, very seldom use masses. We almost always convert to number of moles. So that one is false. The sum of the coefficients on the right is the same as on the left, and that's totally false also. So this one's completely wrong. So the only one that's right is number 3. Next slide. Next. Okay. And here are some notes for what we just said. I'll let you read those at your leisure. Next slide. And then this slide is just basically telling us that whenever you see a G like that right there, or also, I mean, it isn't here on this particular reaction. So for this reaction, we see a bunch of G's, and that stands for gases. So whenever something is a gas or a pure liquid like water or a solid, then you write G, L, or S next to the thing. And then technically, you're supposed to do the same thing for aqueous solutions. So if you had, for example, salt water, sugar water, then you would write AQ, where that AQ is just telling you that you've got something dissolved in water. Next slide. So stoichiometry, as we said before, when we write a number in front of one of the molecules or atoms in a balanced chemical reaction, that number is called a coefficient. And the ratio between the coefficients is called stoichiometry. So this is really the meat of this chapter. Let's go to the next slide. We're already at 1 hour here. So I'm going to have to go ahead and keep going kind of quickly through this. So stoichiometric calculations are the calculations that are relating the numbers in front of the different things in the reaction. Next slide. And I'll let you look at this on your own. Next slide. So the coefficients in a chemical reaction mean two things. They also, in addition to the fact that they mean the number of molecules or atoms that are reacting, they also mean the ratio of the different number of moles that are reacting. Next slide. All right, so first of all, let's take a look at this one, and we'll slow down just a little bit here. So consider the following reaction. P4 plus 5O2 gives 2P2O5. First of all, let's check this to make sure it's balanced. So we have 4 P's on the left, and we have 2 times 2 is 4 P's on the right, and we have 5 times 2 is 10 O's on the left, and 2 times 5 is 10 on the right, so we're balanced. Now they're saying if 6.25 grams of phosphorus is burned, what mass of oxygen does it combine with? So what we're supposed to do is realize there would be a 1 there. If they're going to write something there, it would be a 1, but they just don't write the 1 because it's implied. And so what we're looking at is the relationship between those two numbers, the 1 and the 5. And that's called stoichiometry. The numbers are called coefficients. The relationship between them is called stoichiometry. In this particular problem, we are going to skip a step that we always should do first. And so actually, let's include that. What we want to do first always is find what's called the limiting reactant. But in this case, we don't have to do that because they're telling us that we're going to figure out how much of this reactant reacts with this reactant. And so we don't have to worry about that. But we will on all the other problems, basically. So what we need to do is just look at this relationship between the 1 here and the 5 here. All it means is that for every one of the P4s I have, in moles, not in grams, then I have to have 5 of the O2s. And let me say that again. In order to produce 5 O2s, I have to have 1 P4. And this is in number of moles, not grams. So it doesn't mean that you can start with this number right here because you can't. So they're telling us we have 6.25 grams of P4, where the phosphorus, it says here it's not P, it's P4. So what we have to do is look at the chart and find the mass for P, and whatever it is, we multiply that by 4, and that's going to give us the mass of P4. So it's actually a molecule. If I'm remembering correctly, the P4 is actually shaped like a box with a P at each corner. All right, so once we figure out how many grams per mole we have for P4, we divide how much we have, which is 6.25 grams, divided by that mass. Okay, and that's going to give us the number of moles we have of P4, and then we're just going to need to multiply that by 5, and I'm making a little bit of racket here because I'm going to have to sit down. We're going to multiply that by 5 because for every one of the P4s, we have to have 5 of the O2s. And that will give us the number of moles of O2. And then all we have to do at the very end is convert the moles of O2 to mass. So rather than to keep talking about it, let's do it. So next slide. So we start off with how much we have of the P4, and that is 6.25 grams, which was given to us in the problem statement, right? It's right here. Now look up phosphorus in your chart, and it looks like it's 31 grams per mole. But be sure you check that to see how we got that, okay? So phosphorus, let's see, if we divide that by 4, we get 31, yeah, so 31 grams per mole. And I'm going to pause this for 1 second. Right, okay, so we divide how much we have by how much 1 mole weighs. So 1 mole of P4 weighs 124. How much do we have? 6.25 grams. So 6.25 grams divided by 124 gives us the number of moles, which is what we want. We wind up with 0.0504 moles of the P4. So we will have to have 5 times that much, because for every one of the P4s we have to have 5 of the O2s. So we have to have 5 times as much of the O2 in terms of the moles. So multiply that number right there by 5. And when you do that, you get 0.252 moles of O2. And that's basically your answer. Okay, you'd have to have 0.252 moles of the O2 to react with all the P4. Now, what we're going to do from now on, basically, with a few exceptions, is we're going to have to figure out which one of these would run out first. And that's called the limiting reactant. But we don't have to do that here because all we're doing here is we're just trying to figure out how much of the O2 we would need. All right, so having said that, we basically have the problem finished, but they didn't ask for the number of moles of oxygen. So look back at your problem statement. They want to know the mass. Mass means grams. So, but it's a very simple, trivial step to finish it. All we have to do is multiply the number of moles of O2 times its mass in terms of grams per mole. And that would be 32 grams per mole because O is 16, but this is not O, it's O2. So 2 times 16 is 32. So we multiply the 0.252 here times 32, and we get 8.07 grams. Next slide. All right, so as we've alluded to, a limiting reactant is going to be one of the 2 or 3 reactants that runs out first. And the reason we have to figure it out is because we need to use that one when we're doing the rest of the calculations, because that's the one that's going to run out first. And if we don't use that one, like if you've got A plus B and B is going to run out first, you want to use B to do your calculations when you're trying to figure out how much product you can make. If you use A, you're not going to get the right answer because you won't have enough B to react with it. So the first step in these problems is always to find the limiting reactant, as I said, with just a few exceptions where they tell you, or where they basically give you a scenario where there's only one way it could be. And I'll just give you a hint on one of the situations that could be that way would be when you're burning something. If you're burning something in air, then you're going to assume that you're going to have an excess of oxygen. Okay, next slide. So very quickly, what they're doing here is they're showing us that we're taking a reaction between N2 and 3H2 where everything matches up perfectly. So what we need is for every one of the N2s here, every one of those has to have 3 H2s to react with it to do this reaction. And in this case, over here on the left, everything does have the right number of reactants, because for every one of these, you can see they're all circled here. For every one of these N2s, these things, we have 3 H2s. So everything matches up. So in that particular case, which is extremely unusual, but in that particular case, we don't have a limiting reactant. They're both going to run out at the same time. Whereas on the right, actually, we see what's happened after they have reacted, and everything has reacted. Nothing is left over. Now let's go to the next slide. Whoops, I went too far. Okay, so I can't go back, but on the next slide, if you want to go back on your YouTube video and pause it, it's going to show that one of them actually had too much of it. So the one that there was too much of, you wind up with some extra there. and I can't remember which one it was, but whichever one it was, either the H2 or the N2, when you react all of it all up that you can react, you're going to have something left over. And the thing that runs out first, whether it was the H2 or the N2, is going to be called the limiting reactant. So let's go ahead and move forward now to this slide. The limiting reactant is the reactant that is used up first. Next slide. So let's go through this one kind of quickly because we need to move on to some bigger and better things. So here, first of all, they're giving us a reaction. So get used to looking at these and recognizing these are chemical reactions. 2H2 plus O2 gives 2H2O. So first of all, let's do something that's a pretty good idea to do every time, and that's to make sure it's balanced. So on the left, we've got 4 H's, and on the right, we have 4 H's, and on the left, we have 2 O's, and on the right, we have 2 O's, so it is balanced. So let's go ahead and move forward. Which of the following reaction mixtures could produce the greatest amount of product? So to do this, what we need to do is realize that for every one, and there's no one there, but you can just imagine that it's there, every one of these, you have to have 2 of these to react with it. For every O2, you would have to have 2 H2s to react, right? So of these possible choices that we have listed here, which ones of those involve that much? Well, if you have 2 moles of H2, then you could only react 1 mole of O2. And if you have 2 moles of H2, again for B, you could only react 1 mole of O2. And for C, if you had 2 moles of H2 and only 1 mole of O2, you could react only 1 mole of O2. And then if you had 3 moles of H2 and 1 mole of O2, you could still only react 1 mole of O2 because you could only react 2 of the moles of the H2. So the answer here is that all 4 of these, and you may want to look at that again if you didn't catch that, all of these produce the same amount of product. They're all going to produce 2 moles of H2O. So the reason is because here for A, this H2 is going to run out first. So you're going to be left with 1 mole of O2 that you didn't use. For B, it's the same thing, except you're going to wind up with 2 moles of O2 that you didn't use. For C, you're going to have exactly the right amount of H2 and O2 to match perfectly, so you'll wind up with exactly, and I think I said 1 mole of H2O. If I did, I meant to say 2. I'm not sure. But you can make 2 moles of H2O. So if I said 1 earlier, that's a mistake. For D, you can make, again, exactly 2 moles of H2O because 1 mole of the H2 is going to be extra. So the answer is for all of these, you can make 2 moles of H2O, so the answers are all the same. Next slide. Next slide. Next slide. And I'll let you read this on your own. So next slide. All right, now we're getting into the meat of this chapter. You know that chemical A reacts with chemical B. So we've got A plus B, which, I mean, just, we don't really have time for this, but I'll just real quickly write A plus B. And then it's going to make something else, which we don't know what the other thing is. All right, so we're reacting A with B, and they're saying we react 10 grams of A with 10 grams of B. And what else do we need to know? So what they're asking is, what else would we need to know? What other information do we need? Well, we need to know basically what the stoichiometry is, because, I mean, is this a 1 or a 2 or a 3 here? Same thing here. And then also, we have to know the molar masses of A and B, because it makes a difference, because that'll tell us how many moles we have. So we need to know the molar masses for A and B, and we need to know the stoichiometry. Next slide. Next slide. Okay, so here they're telling us the answers to those questions that we just asked. So they're saying, okay, here's the molar mass of A. It's 10 grams per mole. And the molar mass of B is 20 grams per mole. And the reaction is A plus 3B gives 2C. And they want to know how much of the C can we make. All right, so to do this kind of a problem, it's first of all necessary to figure out which one of the 2 reactants is going to run out first, which means, is A going to run out first or is B going to run out first? And we notice when we're asking this question, For every A, we have to have how many B's? We have to have 3, right? All right, so let's figure out how many moles we have of A. We have 10 grams of it, and it weighs 10 grams, so we have 1 mole of A. All right, so let's look at B. We would have to have 3 moles of B, right, to react with 1 mole of A, because it's got a 3 in front of it. So how much B do we have? Well, we've got 10 grams, and we want to divide that by its molar mass, which is 20. So 10 divided by 20 is 1/2 of a mole. So for the B, we've only got 1/2 of a mole. But we need 3, because we have 1 mole of A. So, but for every A, we need 3 B, so we'd have to have 3 moles of B. Do we have 3 moles of B? No. We just said that we only have 10 grams of it, which is only 1/2 of a mole, because it turns out it weighs 20 grams per mole. So which one of these two do you think is going to run out first, the A or the B? Remember, if we've got 1 mole of A, we'd have to have 3 moles of B to completely react with it, but we don't have 3 moles of B. We've only got 1/2 a mole of B. So we don't have anywhere near enough B. So the B here is going to run out first. So what I recommend that you do is write LR above the B. The LR stands for limiting reactant. And that way you won't have to keep doing it over and over again. You'll just be able to look at it and say, okay, B is the limiting reactant. What does that mean? Well, it means we're going to use B for the rest of the problem here, because it's the one that's going to run out first. So let's go ahead and do the problem now. It's asking how much C can we make. And so we want to now look at the relationship between that 3 and that 2. For every 3 of the B's that we have, we can make 2 of the C's. Let me just say it again. For every 3 of these that we have, we can only make 2 of these. So we can only make 2/3 as much of the C as we have of the B. So we're going to have to multiply how much of the B we have times 2/3. This is not difficult, okay? It's just looking at the numbers and just getting the relationship right. For every B that we have, we can only make 2/3 of a C. So to figure out how much C we can make, we multiplied 2/3 times however many moles we have of B, but we already said we have 1/2 a mole. So 2/3 times 1/2, where the 1/2 is how many moles we have of the B, that's going to be 2, equal signs take forever to make. It's going to be 2 times 1 is 2 on the top, and 3 times 2 is 6 on the bottom, which reduces from 2/6 to 1/3. So we can make 1/3 of a mole of C. Okay. All right, so we can make 1/3 of a mole of C, and that's all you have to do. So there's, again, nothing difficult at all about this. So I think what happens sometimes is people let this stuff psych them out. So just relax and just realize this is not difficult. Now, you can't stop here because they didn't ask for how many moles we could make of C. They want the grams. Remember, they say that what mass of product can we make? So just to finish it, just multiply 1/3 of a mole times how much 1 mole weighs. And how much 1 mole weighs was given in the problem statement here. It's 25 grams per mole. So 1/3 times 25 is your answer. So just take your calculator, divide 25 by 3, and you get 8.33 grams. Next slide. Percent yield, we've talked about this before. Next slide. It's just, what we talked about actually was percent mass, but this is kind of the same thing. Percent yield is when you're doing a reaction. So instead of instead of dividing the mass of what you're interested in by the total mass, you're actually dividing the mass that you actually got from the reaction by how much you would get in a perfect reaction. So if you look down here at the formula here, the mass here that's called the theoretical yield, that's how much you would get if you had a perfect reaction. And I can't go back, but if I did, remember on that previous slide, we said that we could have made 8.33 grams. That's how much we could have made in a perfect reaction. But reactions are almost never perfect. In fact, they're never perfect. So, I mean, we might only make 6 grams instead of the 8.33. So if we want to get the yield, we would divide the 6 by the 8.33 and then multiply by 100%. So 6 divided by 8 is about 3/4, so that's about 0.75. So it'd be about 75% yield. All right, so that's all there is to this. Let's go to the next slide, and we'll have an example of this later. So for example, if we do an experiment and we actually got 80 grams where we figured we could have gotten 100 grams, if we did the experiment in a perfect environment, then the yield would be just 80 divided by 100, which is 4/5, which is 80%. So that's all there is to this. Now, we're going to have to use this in some problems where it'll be a little more complicated than this. But this is basically all there is to percent yield. You just divide how much you actually made in a reaction by how much you could have made in a perfect reaction. And when we say how much you could have made in a perfect reaction, we're talking about like when you're doing it theoretically or on paper ahead of time, like the way we did with the reaction that we had the A and the B and the C. Okay, next slide. So here we're going to get a chance to do this. So, and we're going to have to, all right, anyway, so I want to keep this under an hour and a half if I can, but I may not be able to get that exactly. But, all right, so we have P4 plus 6F2, and I'm just going to look at this real quick and make sure it's balanced, and it is. So here's our reaction. P4 plus 6F2 gives 4PF3, where these are the products over on the right-hand side of the arrow. Here's the arrow, and these are the reactants. And we want to know how much mass of P4 would we have to make 85 grams of PF3 if the reaction has a 64.9% yield. So this is going to have to be done in 2 steps. First of all, we're going to have to figure out how much we're going to have to try to make of the product given the fact that we actually got 85 grams of it and the yield's about 2/3. So what that means is we're going to basically set up a ratio and proportion where we've got, I'm going to change this up just a little bit and say this is about, I'm going to change the 64.9 to 65, and then I'm going to change it to 67 because it's almost the same and it makes it a lot easier to look at what's happening here. 67 over 100 is what we would have if we have 67% yield, so it's a little less than that. But the reason I'm writing it as 67 is because then I can reduce 67 over 100 to 2/3. Okay, and then when we do the actual answer, we'll do it with the real numbers. And so what we're saying here is basically, let's put a little squiggly here to make sure that's not equal. It's approximately equal to 2/3, or actually this is approximately equal to 2/3. Okay, and so what we can do is set up a ratio and proportion where we say, okay, we actually got 85 grams. So how much would we have gotten in a perfect reaction? Well, we don't know that because they don't tell us that. So we're just going to call that X. And so what we have here, this part right here is called a ratio and proportion, and I made it easier. So the way you do a ratio and proportion is you cross multiply. So you say 2 times X equals 85 times 3, which means 85 times 3 is 255, right? And then divide 255, that's 128. So it would be about 128. So you do this on your own, okay? And you should get about 128 for X. And what that means is that 128 is actually going to be your theoretical yield. In other words, it's what you would have made in a perfect reaction. But we need that number to use for our calculations here. So anyway, do it on your own. It actually isn't 128, but it's in that ballpark. So I'm guessing it's going to be a little bit less than that. All right, so now that we know how much of this stuff we have to try to make, we look at the stoichiometry, and for every 4 of these that we actually make, we only need 1 of the P4. So in other words, if we need to try to make 128 here, but before we do that, we actually have to get this converted to moles. So this is 128 grams. So this is how much we're trying to make, but we need to get that into moles. So it turns out that the molar mass of PF3 is 88. So we would have to convert this 128 grams to moles. And the way you would do that would be to divide how much you have, which is 128 grams, by how much 1 mole weighs, as always. So it would be 128 divided by 88, which is going to be roughly, I guess, 1.5 moles. So let me write that here. And it's not exactly, I'm just giving you a ballpark. We're going to have to try to make about 1.5 moles of the PF3. And let's write MOL here, even though it's going to take a long time. So we need to try to make 1.5 moles of this. But remember, for every 4 of these that we make, we only need 1 of these. In other words, we only need 1/4 as much of the P4 as we have of the PF3. So we're going to then multiply this by 1/4, just divide by 4. And that'll give us the number of moles we need of the P4. And then you're basically done. All you have to do is convert moles to grams, and you're finished. Okay, let's go to the next slide and look at the actual numbers. Okay, so here are the actual numbers. Let's keep going here. So here, when you actually solve for x, let's see, I said 128, I think, and it's actually 131. Okay, so that's the yield in grams. But so we would have to try to make 131 roughly grams of the PF3 product. But to do the stoichiometry calculations, you can't use grams, so we have to convert this to how many moles would that be of the PF3. And to do that, you have to take the number of grams you have divided by how much 1 mole weighs, which I'm underlining here at the top. So divide 131 roughly by 88. So next slide, let's see, next, okay, here we go. So 1.5, which I think that's what I actually said. So about 1.5 moles of PF3. Okay, so that's how many moles we would have to try to make. So if this seems like a lot, well, if you're a first semester chemistry student, it is going to seem like a heck of a lot. So you may have to look at this one 4 or 5 times before you really get it figured out. But now, basically at this point, what we want to do is we want to know how much of this stuff do we have to react to get 1.5 roughly moles of the product. So again, for every 4 moles of this that we make, we only need 1 mole of that. So we only need 1/4 as much as we have here, a number of moles of P4. So let's keep going here. So we want to multiply 1.488 times 1/4. Next. So at the end of the day here, after we divide 1.488 by 4, we get 0.372 moles of this stuff over here is how much we would need. And that basically wraps up this problem, except we just need to get it in the units the answer wants it in, because they're asking for mass, and they usually will. But once you get to this point, you're basically done with the hard part of the problem, because now all we have to do is say, okay, 0.372 moles of P4, multiply that by whatever the mass is of P4, which it was on the previous slide. And I can't remember what it was, so I'm not going to guess. So let's go on to the next slide here. 124 was what it was. So multiply 0.372 times the mass of the P4, which is 4 times 31, which was the mass of 1P. So it's P4, so it's 4 times that is 124. And when you multiply the 0.372 times the 124, you get 46.17, or rounded to 46.2 grams of P4. So a heck of a lot of work to do this, at least it may seem that way. But after you go through this 2 or 3 or 4 times, then it will become kind of like easier for you to do it. And if you go through it enough times, it'll become second nature. Okay, so that was the hardest problem in this set. Let's go on and finish it now. Just have a few more slides. Next slide. All right, so this one is another kind of difficult problem, and I'm going to go through it just basically intuitively. We'll get the actual answer at the end. It turns out that this problem is kind of hard, at least in terms of the way it seems when you read it. This is 2 parts. First part, we're supposed to balance this. We have a reaction here, and we have a reaction here, and we're supposed to balance them first of all. So in order to do that, what we're going to wind up having to do is put a 2 here, and then that is going to give us 4 O's, so we're going to need a 2 here. And then just do the same thing here for the H and the N's here. So for the H's, we have 3 on the left. So let's see, for the O's, we have 2. Anyway, I'll let you guys look at this one on your own, and it's actually on the next slide. And since we're almost out of time, what we're going to do first of all is just balance these. And then after that, we're going to have to do a problem, and I'm going to go ahead and move on so we can get to the problem and finish this in like an hour and a half. So next slide. So when you balance the first one, it's just as I said, it's 2 here and 2 here. The second one turns out to be a little bit harder because you end up having to put numbers here, 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 and here, and we usually wouldn't leave that 5/2. In this case, usually I think they do because of the way it turns out. But I mean, so if you wanted to get rid of the 5/2, you multiply all those numbers by 2, but we're not going to worry about that right now. Now, I'm going to keep it right here and finish this. So, I mean, I've got like 7 seconds to do this, but obviously that's not going to happen. But I'm going to go ahead and run through what we have to do to solve the next part of the problem. So we'll be done at that point. You'll be glad to hear maybe. So what they're going to ask us in the next part is they're going to say, okay, if you have 1 gram of this and you make some water out of it, how much NH3 would you have to make the same amount of water? So what we're going to do here is basically using these balanced equations, we're going to assume that this amount of water and this amount of water here are the same. And again, I'm not doing the part that we see in front of us on this slide. I'm doing what's going to be on the next 2 slides. So we're going to assume that these 2 amounts of water are the same. So I'm going to show you an easy way to do this problem, but you'll probably want to not only learn the way I show you, but also learn it the long way. And also notice here that we're doing these with O2. So what we're doing actually, even though they didn't tell us that, they tell us it reacts with the oxygen in the air, but actually, well, actually maybe it does in this case. But anyway, the bottom line is that we're going to have an excess of this. So for this particular problem, you don't have to worry about finding a limiting reactant. And that's usually going to be the case whenever you have an O2 as one of the reactants. So because we've got O2 as one of the reactants, we don't have to take the step where we find the limiting reactant. We're going to assume that the CH4 is going to run out a long time before all the oxygen in the atmosphere runs out, right? So we're going to put LR here just so you can kind of get used to doing that. So LR CH4, which is methane, is going to be the limiting reactant. Now, they're going to tell us that we're going to have 1 gram of this. Let me find a place to write it. So 1 gram. Now, that's not moles, it's grams. CH4 weighs 16 grams per mole, 12 for carbon and 4 for the 4 hydrogens. 12 plus 4 is 16. So I'm going to do this a kind of a simple-minded way. And this will help you to get used to doing stoichiometry problems. So I'm going to write 1 here, even though they don't have it. Because it's implied there, and for every one of these we can make 2 waters, and in this case the water's what we care about because that's what they're asking about up here in the problem statement. Well, actually it's on the problem statement on the next slide. So anyway, that's what we care about. All right, so if we have 1 gram of CH4 and it weighs 16 grams per mole, if I divide how much I have by how much 1 mole weighs, I get 1/16. And I could change that to a decimal, but I'm not going to, for reasons that I think will become obvious as we go through the problem. For every one of the CH4s that reacts, I can make 2 waters, and that's what I care about. So if I start with 1/16 of CH4, how many 16ths can I make of the water? 2, right? 2/16. I can make twice as much. And so I'm going to just carry that right down here to this other reaction. I'm just going to replace that with 2/16, or let's call it 1/8, because it's the same thing. 1/8 of a mole. Remember, these are not grams now, these are moles. So it's 1/8 of a mole of water, and that's the same on the top reaction and the bottom one. So the relationship here, so what I'm trying to do here is I'm trying to make 1/8 of a mole of water in this reaction. And so I'm not even going to have to worry about any of these other numbers down here, again, because I know how much water I'm trying to make, because they said in the problem statement that we'll see in a moment, they're saying that we're going to assume that the number of moles of water is the same here on the top and here on the bottom. So I had 1/8 of a mole on the top, so I'm just going to move that down here and say that this is 1/8 of a mole on the bottom. So now we're almost finished. We just look at the relationship between that 2 and this 3. In other words, for every 2 moles of NH3, I can make 3 moles of H2O. So to find out how much of the NH3 I would have to make 1/8 of a mole of water, I just multiply the number I want, which is 1/8 of a mole times 2/3. So 2/3 times 1/8 And that's going to give me the number of moles of NH3 or ammonia that I need. So multiplying across the top, 1 times 2 is 2. And across the bottom, 8 times 3 is 24. So I've got 2 over 24, which reduces to 1/12. And that's basically your answer in terms of number of moles. You would need 1/12 of a mole of NH3. Now, to finish the problem, which I'm going to do because we're out of time, N is 14, so I'm looking at NH3. N is 14 and H is 1, but we've got 3 of them, so 14 plus 3 is 17. So it weighs 17 grams in 1 mole, and I want 1/12 of a mole. So multiply 1/12 times 17, and you get 17 over 12, which is what, 1.4. Let's go on to the next slide. Well, I think it's like 1.4 grams. Next slide. And then let's just keep going. Next, and actually I was right. It's 1.42 grams of NH3. So what I've done is I've come all the way down to the bottom because we've actually done all the stuff that was on both of these slides. All right, so this is going to wrap this up, and I'm going to have to stop it because once they get past an hour and a half, they get like unwieldy. So let's cut this short. We finished up everything. I think there's an end slide here. Let me go to the next slide. Next, and there we are. So for Chapter 3, we're finished. The main topics were figuring out what is a mole. We said that it's 6.02 times 10 to the 23rd of anything. And then we talked about balancing equations, so be sure and do some practices on those. And then also we did some stoichiometry problems. And actually, you'll be kind of glad to hear that the problems that we just did in stoichiometry, where one of them involved the theoretical yield and the other one involved doing some variations between 2 different reactions, those are probably actually harder than most of the ones we'll have to do. So we'll be going to the work problems for Chapter 3 next. So I'm going to go ahead and stop, and I'll see you in the work problems.